In the first moments after the birth of the universe, matter was nothing like what is now seen in stars, planets, or galaxies. Before protons, neutrons, or atoms existed, the cosmos was dominated by an extremely hot and dense state formed by elementary particles that moved at speeds close to that of light. Understanding how this primitive matter behaved is one of the great challenges of modern physics, because it offers clues about the conditions that governed the origin of the universe. If you are interested in this topic, do not forget to subscribe and give like to receive more related content. A new study carried out with data from the CERN's Great Hadron Collider has made it possible to explore this early state of matter by briefly recreating it in the laboratory. The research, published in the journal Physics Letters B, analyzes how high-energy particles interact with quark and gluon plasma. The theory that describes these interactions predicts that at extremely high temperatures, quarks and gluons cease to be confined within protons and neutrons. In these conditions, a state of matter called quark plasma and gluons arises, which dominated the universe during its first microseconds. The particle accelerators allow this environment to be recreated for a brief moment. In the Great Hadron Collider, heavy cores accelerate to speeds close to that of light and collide, releasing an enormous amount of energy that generates a small drop of quark and gluon plasma. During that brief moment, detectors record thousands of particles produced in the collision. Analyzing their trajectories and energies allows indirectly reconstructing the properties of plasma and understanding how high-energy particles interact with this extreme medium. The work focuses on events where a Z boson occurs, which interacts little with plasma. This makes it an experimental reference to study what happens in the surrounding environment, allowing physicists to investigate how the medium responds to the passage of a part. The analysis reveals a characteristic pattern in the distribution of particles produced. A decrease of particles is observed in the direction of the Z boson, and an excess in the opposite region, indicating the response of the plasma to the passage of the parton. The study concludes that the observed differences between heavy ion collisions and protons provide a clear sign of the interaction between parton and plasma. This confirms that quark and gluon plasma collectively responds to disturbances. Although this result is solid, more accurate statistical measurements will be needed to discriminate between the different theoretical models. However, the work opens a new way to study the properties of quarks and gluons plasma.